The ENVI analysis tool for calibration and correction normalized for lamp spectrum. So this is a feature that we've built in to the software to where you are able to record the lamp, the Dollinger light source that you have, the halogen lamp. You're going to do a small hyperspectral scan of this lamp, maybe just 21 lines, a quick scan. Then you're going to take a region of interest and get an average. Then you're going to take that average and normalize it to a value of 1 using spectral math, and we'll go over that here. And then we're going to use that normalized spectral plot that we're going to save as a spectral library file. It's going to represent the lamp across the whole area of the camera, of the chip, and of the spectrograph. And then we're going to take every pixel in this image here I have open, and we're going to divide this normalized lamp spectrum into every pixel to get a normalized spectral readout from every pixel. So if we think about this for a second, every pixel in this image is showing the scatter off whatever it's scattering off of. In this case, it's these carbon nanotubes. And it's showing some spectrum. However, there are certain materials that definitely reflect the light in a certain manner, like gold particles, noble metals, those kinds of particles, have some kind of plasmonic peak, and we've seen that in other tutorials. We see these plasmonic peaks, these resonant peaks, and it's very easy to map and identify those. If you're doing some kind of spectral characterization work where you want the true spectrum of something, a lot of people will choose to do this lamp normalization. Basically, it takes the influence of the lamp with the instrument response out of the spectral data, giving you a pure reflectance spectrum. So a lot of times it's necessary to use this when you want to get the true spectrum of something if you're doing some kind of characterization. Or perhaps you have a particle or some material that doesn't really have a super unique spectrum. It's kind of got this spectrum that's similar to the lamp in some cases. That can happen. So this will tease out those minute differences even more by doing this routine. So I've already got the lamp scanned here. As you can see, it's just 21 lines of data. If we look at the spectrum, it's pretty uniform across the entire field of view here of the camera from one side of the chip to the other. It's a little intensity variation here, a little more intense in the middle. We kind of expect that. So what we're going to do is we're going to create a region of interest, take out the ROI tool, and I'm going to go to rectangle. I'm going to, in the image window here, I'm going to draw just a box all the way across here, double click and fill it in. And it's 14,000 pixels. I'm going to hit stats, this button here. And this is going to take a second, but what it's going to do is it's going to give me the maximum, minimum, plus and minus standard deviation, and most importantly, what we need is the mean. And we're going to take this mean spectrum of all these pixels, and we're going to take this one spectrum, isolate it, and do some spectral math on it to normalize it to a value of 1, because it's going to have, obviously, the mean intensity. So it's always important when you do this scan to have some good signal. Anything over 1,000 is good. I think this was around 3,000. This should be fine. So this is still working here. It's a lot of pixels. Okay, it's finally done. So we right-click and show the plot key. If we right-click again, we can go down here to Options, New Window, Blank. We have this blank plot window, and we can just click and drag this mean right into there. So now we don't need this anymore. We can actually close the lamp scan. We're done with that. So what I want to do to this mean spectrum of the lamp here is I want to normalize this to a value of 1, because right now it has an intensity. We need to have it normalized to a value of 1 so it works in the equation for the normalized for lamp spectrum equation that automatically runs. It needs to be a normalized spectrum. So the way we do this is we go to Basic Tools, Spectral Math. And On the desktop of your computer, there should be a folder called Equations. Here it is. And normalize to peak. These equations will be on your desktop. And the normalize to peak is float S1, which is spectrum 1, this will be the pixel in whatever image you're correcting, divided by the maximum of that. So this will be to normalize this peak. So we highlight it to put it into the expression column. And we're going to do it to this mean region here, and new window. And here we go. So now we have a normalized lamp spectrum. So we want to save this as a spectral library file. Highlight the one spectrum. I'm just going to put this on the desktop and call this lamp. Okay. I'm going to put SLF. Okay, so when would you need to do this in terms of your lamp? I would make a lamp spectrum at the beginning of every experiment, every time you change the bulb for sure. Just kind of try to keep track of that somewhere in your lab book. So now I have this and it's saved. So now we want to correct the spectrum for these pixels in this image. So we go to the Site of Viva analysis, calibration, and correction, normalize for lamp spectrum routine. First we have to give it an image, and we're going to use this WTATP60X file here, and a lamp spectrum. So I saved it on the desktop, lamp 1420. And usually what I do here is I will name it the same file. So WTATP 60X-2, and then I will put capital CORR for corrected, and we hit OK. So this will produce a new image that looks just like this one. Except, and remember we can link these so we can see exactly in the same area. Show the spectrum. This is the corrected one. And this is the non-corrected one. So, first thing you will notice is that there is a lot of noise at the ends of the spectrum. This is because when the correction math runs, it amplifies the noise. So as this dips down here and dips down here, this becomes very noisy. So the best thing to do is you can subset either the plot you're looking at, or you can subset the whole data cube. I choose to subset the whole data cube, and the way we do that is we go to Resize Data, Spatial, and Spectral. This was in one of the earlier ENVI basic tutorials. And I'm going to highlight the corrected one, and then we want to do a spectral subset. So normally I will subset somewhere between 450, I'm just going to hold down Shift, and about, I guess in this case we'll try 850. So I usually name it the same thing, corrected, except I'll put in subset. So now we can close this corrected file. So now we have a subset. And I'm going to link 2 and 3. Already closed the other one. And so now we see, I don't see that noise at the end as much. So to be completely accurate to compare these two spectrums, we're seeing the full spectrum here. If you don't want to subset the original just for comparison, you can always just go to Edit, Plot Parameters. And here we can say, 450 to 850. This is just subsetting it on the display plot, not on the actual data. Yeah. So if we look at this after the lamp, this peak is around 616, where out here it's more around 670 or so. So the peak did shift due to the lamp correction. So this is how the lamp correction routine works. If you're just looking for particles and you're wanting to map them in cells or tissue, and you get plenty unique signal enough, a unique enough signal to map your particles and identify your particles, then you might not necessarily need to do lamp correction. If you're having trouble distinguishing two different particles that are very similar, perhaps you have a carbon nanotube and one is coated and one is uncoated, and you're seeing the spectrum looks very similar, try the lamp correction and see if that teases out any differences. Or if you're doing any spectral characterization where you're wanting to know the true reflectance spectrum or scatter spectrum off these particles or materials, this is definitely something you're going to want to do. So that concludes the tutorial on the spectral normalization and correction for the lamp. Have a good day.